Okay, we are now recording. Let me go back to the PowerPoint. I meant to do that before we started recording, but I forgot to. And we'll go from current slide. I thought I already had this set up, but here we go. Okay, now before we get to example 5, let me give you my excuse, my apologies for being late getting started today. I was scheduled to have another treatment. I don't know if you recall, I had a treatment a month ago. Um, my counts had gotten really high, really high, and I had gotten somewhat anemic, and because the white cells were crowding out the red cells, all that kind of stuff. So I had the treatment. It was a Thursday and Friday. They gave me a 10% treatment on Thursday and a 90% on Friday. This was about a month ago. And on Thursday, I could just feel the battle roaring inside, and I knew it was being a very effective treatment. And I was almost scared. I got so hot when I was in the chair, I was eating ice just to keep from feeling so terribly uncomfortable. I was afraid I'd throw up or something. And anyway, it went well. Friday, I went in for the 90% treatment. I said, boy, if that was a 10%, what's this going to be like? Well, it was almost nothing. I mean, yeah, I could tell some stuff was happening, but it wasn't nearly as intense as Thursday had been when it was only 10% of the treatment. So but right before the treatment and then certainly right after the treatment, I was exhausted. And I knew they had already told me I was very anemic at the time. I think I told y'all that too. And afterwards, I knew I was even more anemic. And I would get winded going upstairs or actually bending over. I mean, anything was enough to knock me out. And so it was pretty rough for a while. And you know that I've had to stop and say I've got to get some caffeine or sugar or something to keep going because I was just so exhausted. Well, I knew that was happening, but it had been getting better every day. But then they had scheduled me for another treatment on Friday, and I wanted them to see my counts before I got in the chair on Friday. So I asked them, I sent them a message on the portal and said, can I get my blood work done on Wednesday? So, because I'm still very, my stamina is very low, can we do that? And I sent that on Sunday evening. They didn't respond all day Monday. And finally, yesterday afternoon, they said, yeah, you go on and have your blood work done. So I went in this morning to get the blood work done. And it was when that blood work came back, I got a phone call immediately. I missed the phone calls because I was driving, but I was and this is a month after the treatment, okay, or close to a month after the treatment. It would be 4 weeks this coming Friday. That I am such still my red cell counts are so low. They want to give me a transfusion on Friday. They wanted to do it tomorrow, but I said, no, I've got classes tomorrow. So they're doing that on Friday. They need to give me shots to boost my immune system. They can't do it today, but they're going to do it Friday. So everything I was feeling, it's even worse than I felt like it was. So it was, the nurse called when in between these two classes. So I had to talk with her and get all the details worked out, where to go, when to go, that kind of stuff. And then I thought I had time to call Dr. Pruitt on campus to let him know what was going on because I talked with him this morning when I was there getting the blood work done. Things were running more slowly, so I was letting him know that I wasn't in my office. And so we talked for longer than I should have, and then I realized I was already late for class. So sorry about that. But when I was saying I needed some soda or something to keep going, I really did. I was afraid it was just had become a crutch, It's more than a crutch. It was real. So anyway, sorry about that. And if I do have to run down, I forgot to bring my soda up when I came up just now, but I think I'm okay. I ate enough carrots in that little bit of time I had to eat uh, between the phone calls and stuff, that I think I'll have enough energy to make it through today. So anyway, sorry about that, folks. No real bottom line for you except for this. I will not be in the office this afternoon after 5:15. Usually I'm here till 6, but I'll be leaving probably at 5:15 to go get typed and tested for blood work. And then I'll also be going Friday. I'll be getting a transfusion. I wouldn't have been here anyway. I would have been getting a treatment if they had done like they wanted to. Now I'll be getting a transfusion and shots, and that will be Friday. So hopefully I'll be back in the office sometime mid-morning on Friday. So anyway, I'm not going to be as available as my office hours indicate I will be, but I will be around some. Okay. Do y'all have any questions, issues, concerns, problems, anything like that? Okay. If not, let's pick up where we left off last time. That was example 5 at the bottom of page 832. We're in chapter 12, vector value functions. 12.2 is differentiation and integration of vector value functions. We've done the differentiation part. We've got integration part to do now. So here is our first one. Find the indefinite integral, the integral of ti plus 3j dt. Now this plus sign doesn't have to be bolded. Whoever is doing the typesetting kept the bold on too long. They don't need that. That's not a vector addition. That's just a plus sign. Okay? So how do we integrate a indefinite integral? How did we differentiate, a vector value function? We do it term by term. And that's exactly what we do here. We integrate ti, well, the antiderivative of t is t squared over 2. There's your I component, plus, and that doesn't have to have an arrow over it. Antiderivative of 3 would be 3tj. Okay, oops, except you don't need the integral sign. Sorry about that. Okay, and then you put a plus c. Now, the difference about this plus c now, before, when these were not vector value functions, were scalar value functions, or scalar functions they usually call them, then the c was just a scalar, a constant. Now c is a vector, because you see, technically we should have done a t squared over 2i, t squared over 2 plus c1i, and this should have been a 3t plus c2j, and then that would have been a vector there. So rather than plugging them in here and here and having two constants, just make it a constant vector. Okay, it may have components in the I or the J direction, but just make it one. So there is your integration of a vector value function. Let's watch them do it. Okay, integrating on a component by component basis. So like I've said lots of times, everything is done in vector stuff. Do everything component by component, including integration, including differentiation, including addition, including everything. Okay, maybe not multiplication and division, but most things we do component by component. Okay, so you integrate t, and that's t squared over 2, bring the I along, integrate 3, that's 3t, j, bring the j along, and then rather than having a constant, scalar constant, you now have a vector constant, which probably has an I and a j component. Okay, but just call it vector c and let it go like that. Any questions on that? Okay, I think that's the last slide of the program, so Now we'll be going to the whiteboard for examples 6 and 7. Any questions on this before I go to the whiteboard? Okay, and then we'll be through with 12.2. Where is everybody today? I thought surely we'd have people showing up by now. I hope I didn't lose them when I wasn't here on time. But like I said, I was talking to my boss and I couldn't quite get them off the phone. This is such a pain in the neck. I think I'll just go on here. Okay. Let me minimize this. Okay. Discard this. And okay here. I have to redo this every time. Let's go on and close this out here. Okay. This is such a pain. There we go. Close out 12.2 and go to screen share for 12.3. There it is. Now, I have to go back and redo everything I did before. You can't see it, but this taskbar sits right below the middle of the screen, so that's a pain. And we'll go this from current slide. It'll get set up in a minute. There we go. Oh, wait. What was I doing? It's supposed to be on the whiteboard. And now I have to readjust this too. Sorry about this. The old gray cells, they aren't working well today. I mean, number one, it was a shock hearing that I have to have a blood transfusion on Friday. So I'm not completely with it today. So anyway, here's example 6 on page 833. Okay, evaluate this integral. The integral, now this is a definite integral here, from 0 to 1 of r of t dt okay, when the r of t is this. This is the integral from 0 to 1. Now these are the limits on t, not x, not y, not z, t, okay? The parametric equation. So here it is. The cube root, I'm going to write it the way they do, and as soon as I can, I'm going to undo this, okay? Cube root of t, I, remember this ends right there, plus one over t plus 1j plus e to the minus tk. Yeah, this thing is such a pain in the neck. Minus tk, okay, dt. Now, okay, that's your r of t, the thing that's in here. And we integrate term by term. So the first thing I'm going to do before I even start this is write it the way I want to write it, okay? The cube root of t, that's t to the 1/3 power. And that's your I component. We can put that in parentheses if you want to. Now, the j component, I think I want to write it this way. T plus 1 to the minus 1 power. And that's the j component. And then this is perfectly fine the way it is, plus e to the minus t k dt. Now, the only reason I did that is so much easier to evaluate or integrate doing this way. So this is going to be antiderivative of t to the 1/3 would be t to the increase this by 1, which is 3/3. That would be make it to the 4/3 power, and then divide by that new exponent, which is the same as multiplying by 3/4. Okay, that's in the I direction, plus, only this is now going to be a minus. Okay, no, it won't, it'll still be a plus. Okay, increase that by 1. Well, that was a dumb way to do anyway. I could have left this in this form if I had been thinking right. This is just the log of absolute value t plus 1. You see that here, you see it there. Okay, that's just a log, and that's the j component. And then this one will be the minus, because the antiderivative of e to the minus t would be e to the minus t with a minus in front of it. So that's why I went on and did that. And this will be your, that's supposed to be a t there, okay? And that will be your k component. Now notice I haven't put a plus c, even a vector plus c, because this is a definite integral, okay? So I put the limits here from 0 to 1. And I do that for every component. So this is going to be, when you plug a 1 in for the t, the 1 to the 4/3 power is 1. So this is going to be 3/4 minus 0. 0 to the 3/4 power is 0. So it's 3/4 I. I have another phone ringing. I usually don't like to answer phones. Well, maybe I don't. It was my wife. She just left me a text, and I'll deal with her in between classes. Okay, she's just checking on something with my treatments. Okay, plus, okay, log of 1 plus 1 is 2, so that's log 2, minus log 1 plus 0, or 0 plus 1 is 1. Well, log of 1 is 0, so there's our only contribution to this. You don't need absolute value bars anymore, because 1 plus 1 is 2, that's positive. Okay, and then your final one is minus e to the minus 1, then minus a minus, which is plus e to the 0, which is 1. Okay, so actually the easiest term is the one that turned out being the hardest, and this is your k component. So this will be 3/4 I. And just like before, when you do definite integrals, you get numerical answers. These are going to be numerical vector answers, but you don't have the variables anymore. Plus log 2k, log 2j, minus, now let's evaluate this. You could leave it as e to the minus 1 if you want to. I think I will. And make this, goodness gracious. Okay. That may have been something else. Okay. But with all the nurses calling and stuff like this, I have to pay attention to the phone now more than I normally do. Okay. This will be e to the minus 1 and e to the 0, and this is, the minus is here, but if I put it in parentheses, I'm going to put minus a minus to make the plus, plus 1k. Okay, Now let's see how we did. 3/4 I plus log 2k, they actually put this in parentheses. It's not necessary, but j, and then they put a plus, and what they did, they reversed the order and did a plus 1 minus e to the minus 1 k, which is the same thing, because see, minus and minus is plus and minus and plus is minus. So either way will work. Actually, they wrote it this way: plus 1. I was starting to, but I didn't think they'd do it. 1 over e. Sorry, came as a surprise. Okay, so any one of those answers would have been okay. Okay, this answer would have been fine, that answer would have been fine, this answer would have been fine for the k part. These parts are pretty much done. Any question there? Okay. So let's look at example 7, which will also be done here. Sure, there's no questions here. Let me just check one more time. I can't believe we've only got 2 out of 8 students here. This is a much better attending class than that. I sure hope I didn't lose them by being late. Okay, no questions on this? All right, let's do example 7. Find the antiderivative of this. R prime, that's the first derivative of some R function, is equal to cosine 2ti Now in my mind, if they put the log 2 in parentheses, they sure should put that one in parentheses, but they don't, so it's okay. Minus 2 times the sine of t. This is not writing well at all. J plus 1 over 1 plus t squared k. Okay. It says find the antiderivative of this. This is the derivative of a function. We're looking for r then, the antiderivative of this. If I could get my pen to show up somewhere here. There it is. Okay. We're looking for r. Okay. This is r prime. So we're looking for the antiderivative of it. But it satisfies this condition that r of 0, the number 0, is 3i minus 2j plus k. Now there's a couple ways you can approach this, and I'll try to do it the way I see most reasonably. Okay, now you may not like this, the book may do it slightly differently, but the book probably is going to be better than mine. But number one, on this thing up here, I wish I'd have left more room. I wish I could find my cursor. There it is. Okay, this, remember, r prime is dr dt. That's what r prime is. It's just another way of writing that. Well, if you take the dt and write it in differential form, in other words, put the tt after this, then you have this. dr, vector r, is equal to cosine 2t I minus 2 sine t j plus 1 over 1 plus t squared. Pen's not writing well. K. Then put the dt here. Okay, you just take this thing. It's sort of like you're multiplying through by dt. That's an operator. You don't really multiply through an operator, but you write it in differential form, which is what we got here, and then we integrate both sides. Okay? And this is a indefinite integral. Okay? Well, the fundamental theorem of calculus part 1 says the integral of a derivative is a whatever you had to begin with. That's r of t. That's what we're looking for. Okay? The antiderivative. Well, the antiderivative of cosine is sine. But the 2t here, it's sort of like an anti-chain rule. That would be 1/2 the sine of 2t. I'm going to put it in parentheses. I just like to do that. I. Okay? Now, antiderivative of sine would be cosine. So it's going to be antiderivative of sine is minus cosine, so this will be a plus 2 cosine of t j. Now, how do you check these? You just go back and take a derivative, and you see that indeed gives you that. This indeed gives you that. If you take the derivative of it, you'll get that. Okay, now, this next one is a little bit of a problem, okay, because this is not quite so simple, okay? So I'm going to pause for a moment here and work this one out, okay? This will be the integral of this thing here. Well, that to me looks like a trig substitution. Let t equal tangent theta. Okay? Yeah. Then t squared would be tangent squared theta. One plus t squared would be 1 plus this would be, I'm sorry, 1 plus that would be this plus 1. Okay? All right. Now, you also have your dt. It's also a then statement. dt is equal to the derivative of tangent is secant squared theta. Okay? Now, what is 1 plus tangent squared theta? That is secant squared theta. So what do we have here? We have the integral of dt, which is secant squared theta, over 1 plus tangent squared theta, which is secant squared theta. It's just, I forgot this, d theta. Okay, so you have the integral of d theta. That's all, because it's secant squared theta over secant squared theta is 1. Now, that is just theta. Okay, well, what is theta? Theta is the inverse tangent of t. Because t is tangent theta, take the inverse tangent of both sides and you get theta is equal to inverse tangent of t. So, All right. The minus sign or equal signs aren't coming through well. Okay. So what do we have? R of t is equal to 1/2 sine 2t I plus 2 cosine tj plus inverse tangent tk. Now, plus some vector, I'm going to call it C1I plus C2J plus C3K. Okay, that I would have just written as capital C, okay, as a vector. I want to break it down into components. Okay, now we also know that R of 0, our initial condition, you might say, is 3I minus 2J plus K. So I'll go on and write that down. 3I minus 2J plus K. So let's plug in t is equal to 0. Well, when t is equal to 0, sine, well, 2t would be equal to 0. Sine of 0 is 0. 1/2 of 0 is 0. So that gives you 0I here. So I'm not even going to write it down. Here we have plus 2. Cosine of 0 is 1. J. Okay? And here we have plus, when you plug in a 0 here, the inverse tangent of 0 is 0, so that gives you nothing there either. So I'm going to leave that alone. So this is plus C1I plus C2J plus C3K. Now you don't have to do it this way. This, to me, sort of is a way that makes the most sense. Okay? So from looking at here, comparing these, it looks like C1 has to be 3. Okay? So C1 has to equal 3. I wish I'd have brought my Coke up now because I'm so tired. Minus 2 is equal to 2 plus C2. Minus 2 is equal to, comparing the J terms here, minus 2 is equal to 2 plus C2. Okay, which we can solve by subtracting 2 to both sides, and that gives you C2 is equal to minus 4. This is really ugly. And this eraser is way up here. Okay, subtracting 2 from both sides, you get C2 is equal to minus 4. Okay, and then last one, C3 is equal to 1. So C3 is equal to 1. So let's go back and plug those values in here. And what we have is the R of t, I'm not going to write it again because I don't have any room, 1/2 sine, and that S is terrible, sine of 2t plus 3i, because your C1 was 3, plus, I'm sorry, I wish I had my Coke up here. I am so tired I can hardly stand it. Let's see if water will prolong me here. I was hoping the sugars in the carrot and my dip was going to be enough, but that doesn't feel like it's going to be. So your J component is plus 2 cosine t, and then the C2 here is minus 4 J, and then finally you have plus, my writing is really crooked here, tangent, inverse tangent of t, that's a minus 1, tangent of t plus 1 k. Alright, that's what I got. Let's see how they did. R of t was 1/2 sine 2t plus 3i plus 2 cosine t minus 4j plus inverse tangent, they called it arctangent, t plus 1k. Same answer, okay, except they did arctangent, I did inverse tangent. They went through a few more steps or processes to get there. It seems like to me if you just line it up and write it out and then match the terms, you get the same way. If you like the way the book did it better than the way I did it, go for it. You paid for it. You can follow the book as well. I'm still looking to see if I can find any more students. And y'all said you had no way of knowing whether they came early and left before I got here. Sorry about that. All right, that finishes 12-2. Now, not always do I say this, but always I mean to. Always check your concept checks there when you're finished with a section. There's only 2 of them, one on derivatives and one on integration. And think through those, whatever they're telling you to do. Then the homework exercises will be, I think I got something in my eye. Any of the odds 3 through 9, they're all at Calc Chat, 5's at Calc View. Any of the odds 11 through 17, they're all at Calc Chat. I'm so sorry. 19 or 21 are both at Calc Chat. 23 or 25 are both at Calc Chat. 25's at Calc View. Any of the odds 27 to 33 are at Calc Chat. 27's at Calc View. 35's at Calc Chat and Calc View. 37's at Calc Chat. Any of the odds 39 to 45 are all at Calc Chat. 41's at Calc View. 47 through 51 are all at Calc Chat. 47's at Calc View. 53 through 57 are all at Calc Chat. 53's at Calc View. 59's at Calc View. Excuse me, I'm so sorry. Any of the odds 61 to 67 are at Calc View. And then any of the odds 69, either 69 or 71 are at Calc Chat. I don't know what I said before. 61 through 67 are at Calc Chat. 69 or 71 are at Calc Chat, and then 73 and or 75 are true false, and they should be at Calc Chat as well. Okay, I can hardly talk. All right, any questions on 12.2? Okay, I think I'll go on and clear the screen here before I go back and clear I want to clear this. Okay, wait, that's 12.3. Well, we'll just go on and do 12.3. I was going to try to clear 12.2. I thought that's what I was doing, but it came up 12.3. So 12.3, and I tell you what, I do need to take a little break here. In the morning, the sun comes in the window. This is a northeast corner room of the house, so I get plenty of sunlight coming in. But then when the afternoon gets here, it gets chilly. So I've got to go turn up the thermostat a notch or two. So I'm going to pause the recording for just a moment. And I think when I go do the thermostat, I'll go on and get my Coke too, because I think I'm going to need it. So sorry about, we're late getting started now. I'm having to take a break in the middle. So hang on, I'll be right back. If any others show up, tell them I'll be right back. And let me make sure there's nobody else waiting. Oh, we've even lost Kira. Houston, did she say where she was going? Maybe we lost Kira, Houston too. I don't know. All right. In 12.3, we're talking about velocity and acceleration, which hopefully all of you recognize are very closely connected with derivatives and integrals as well. Okay, I can't get the slide to advance. Let's see if there it goes. Here are two objectives. Describe the velocity and acceleration associated with the vector value function, and use a vector value function to analyze projectile motion. Okay. Houston, are you still with me? Well, at least your microphone is, or whatever. So let's move on. I can't move on. I don't know why it's not moving. Okay. As an object moves along a curve or a path in the plane, the coordinates x and y of its center of mass are each functions of the time t. Now, why they brought up the center of mass here, I'm not absolutely certain. Yeah, I guess so. Because if its object is basically two-dimensional or three-dimensional object, so if you talk about center of mass, you're talking about the x bar, y bar, z bar. They're right at one location. So that center of mass follows along as a function of time, t. Rather than using the letters f and g to represent those two functions, that's the x is equal f of g and y is equal to g of t, what they quite often do, and this is very typical of physicists, which tends to drive, I think, mathematicians crazy, is using the same representation for the coordinate x as the function that represents the coordinate x. X is equal to x of t and y is equal to y of t, which I can easily imagine that would drive a pure mathematician a little crazy. I don't care, and I'm guessing y'all probably don't either. Okay, so the position vector r of t takes on the form of r of t is equal to x of ti plus y of tj. Basically, this doubles as being the coordinates. X coordinate is the I value, and y coordinate. I've even lost Houston now, so I'm just talking to myself now. I hope some students will be coming back. I don't know why we've lost. Now, I'm hoping I still have sound. It looks like I do. So I hope the students haven't assumed I'm not here anymore. I am. And hopefully this is recording. I am recording and it is progressing. So I assume that it's making sense. But both of the students who were here today have now left. Sorry about that, folks. But I'll keep going for those of you who aren't here and those of you who were here if you come back to see it. So there's your position vector. R of t is equal to x of ti plus y of g tj. And now it won't advance. Okay. To find the velocity and acceleration vectors at a given time t, consider the point P is x of t plus delta t. In other words, Q is at a place x where it was at x at time t, add a little bit to it. So this is going a little bit beyond where it was at x of t. Y is also gone that same amount beyond where it was at x of t. That is approaching a point, I think I would say this the other way around, P of x of t, y of t, along a curve. The curve C given by R of t. Oh, here's somebody coming back in. I can't see who it is now. James is here. Thank you, James, for showing up. Okay. Okay, we've had odd numbered students today, and we still have them. James, had you tried to get in the class earlier? Okay. I was late getting here today because of a couple of things. I'll explain in just a minute. But when I got here, I only had two students here, Kira and Houston. So I was hoping that because I was late, students hadn't left. And then as I was teaching, I had to, I'll explain this again too, take a quick break and then come back. And when I came back, I had lost Kira, and I kept on teaching, and I tried to communicate with Houston, never got a response from him, and after a while he left. So I just wanted to make sure, number one, that my microphone was working, if they weren't able to get in touch with me. And here comes Kira's back. Good. Glad to see that she made it back. Okay. Because I had to take a quick break, and I guess she must have taken one too. But Kira, we've lost Houston and picked up James, but I don't see Kira yet. I just let her back into the room. Oh, you're there. Okay. For some reason, only one showing up at a time. I don't know why Zoom does this. Okay, but glad you're back. But James has come since you left, so I was just explaining to him what happened, so sorry you have to listen to it again. James, I don't know if you remember, but about a month ago, in fact, it was 4 weeks ago this coming Friday, I had, actually a Thursday and a Friday, I had a treatment for my chronic lymphocytic leukemia. The counts had gotten way, 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 way high. I'd had a treatment last January. When I had a checkup in March or around March, the counts were still on the low side, so he said, let's go another 3 months. Another 3 months came around. They had gotten a little high. By this time it was May, June type time frame. They had gotten a little high, but not dangerously high, and that was back when everybody was really worried and not knowing what to do about COVID. So he said, let's not do a treatment now. So I was all in favor of that. So then I went back in, what was it, September? Yeah, August, September time frame, and he took blood work again, and this time my white cell counts had shot through the roof. Okay. Also suppressed my red cells pretty badly too. So I was pretty anemic and in serious need of a treatment. So he's scheduling a treatment for me, um, and that was about a month ago. So I guess it was October. And because the white cell counts were so high, he had me do it in two pieces. Do 10% of it on the Thursday, and that's why we had to cancel our linear algebra class, and then 90% of the dosage on Friday. Well, that Thursday, before I went in for the treatment, I was feeling so exhausted. So much of the time, the anemia had really kicked in. It had been creeping up on me before. Now I knew what was happening, and I've really felt it. So I got the treatment on that Thursday, that 10%. I could just feel the battle going on inside. I was getting very, very hot. I was eating ice just to keep myself from getting sick for being so hot. And ultimately, by the end of the day, I thought, boy, this was an effective treatment. And then I went in Friday for the 90% dosage. I thought, what's this going to be like? It was nothing as bad as the previous day. So I knew that the 10% had taken care of just about everything, and the 90% sort of wiped up what was left. Well, talk about exhausted. After that, I was completely wiped out. I mean, just totally anemic. I knew they didn't do blood work, but I knew I must be. And so I just struggled through the next 3 weeks. That leads up to this week. They had scheduled me another treatment for Friday. I knew I did not want to have a treatment on Friday, so I wanted them to see the blood work before Friday. So I asked if I could have blood work done on Wednesday rather than waiting till Friday, and they said, well, I sent them that in the portal on Sunday evening, didn't hear anything Monday, and finally yesterday, late yesterday, 5 o'clock or something like that, they finally responded and said, yes, go on and have the blood work done anytime that you want to go by there. The orders will be in. So I went this morning early to get the blood work done. And by the way, I have been feeling stronger basically just about every day. Not much, but a little bit. I still get winded coming upstairs, which I didn't used to do, and sometimes I can hear my heartbeat, and I knew that wasn't good, but I knew it was probably anemia. And I think I've been telling you all that. Well, this morning I went to get the blood work done, and I was not home for very long before they got the word on the blood work, and they were almost panicking. I am incredibly anemic now. And this is nothing like I was right after the treatment. They don't know that, but I know it. And they also, my platelets are way low. My neutrophils, which help prevent diseases, are really low. I mean, really, really low. And so rather than scheduling me for a treatment on Friday, they are scheduling me for a blood transfusion on Friday just to boost everything back up again. So the reason I'm telling you that, number one, is that's why I've been so tired lately and having to interrupt and take, drink some soda or something like just to keep myself going. But number two, my office hours this evening, after we finish our differential equations class for Kira and James, I'll have to leave. I thought I'd have to leave right at 4. They said probably wait till 5:15 to go, but that's still in part of my office hours, so I will not be available the last part of my office hours today because I have to go get typed and tested for the blood work they're going to do on Friday so they can have the right blood there. And then Friday I will not be available for at least the first part of my office hours at all on Friday. Hopefully I'll be back home sometime Friday morning and I'll be here for the last part. But basically, it was going to be, I was going to be in treatment all day, so I was going to say we wouldn't have any office hours on Friday. Now it looks like I may have some. So that's a very long story. I probably took way too much class time to explain, but that's where I am now, and it's just, well, anyway, I'm getting a shot on Friday to boost my neutrophils, and also getting blood transfusion to boost the red cells and platelets and all that kind of stuff. So I should feel better next week, but there are no classes next week. So, but basically we're not going anywhere on Thanksgiving. We had planned to go up to see Karen's mom on her 85th birthday the day after Thanksgiving. Now I think I probably won't be going. Karen will still go, but I won't. And then we're probably not going to do anything at Christmas either. So we're going to not see family, not see much of anybody. So going to be a homebody for just about the duration, I guess. Okay. We have been planning most of that anyway just because of COVID. But now with my situation, I don't think we'll be doing anything. So anyway, too much of that. Now, here's what I don't like about the way they phrase this. To find the velocity and acceleration vectors at a given time t, consider a point q, which is x of t plus delta t, y of t plus delta t, that is approaching a point p of x of t along a curve c given by, and then they give this curve. Okay, that's a lot of blah, 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 but it looks like to me that P would be approaching Q, okay? Unless the delta T is getting smaller. And I think that's what they're talking about, because that's what the picture indicates. But you usually think of this, if this is T plus delta T, that's further along than what P is, because that's just at T. But now they're saying Q is approaching P, and that's because your delta T is getting smaller. We're used to that, okay? So here's the function. The R vector here is the vector from the origin to P, and there it is to Q. So this is R at T, here is R at T plus delta T, okay? Now, the difference here between P and Q is what we call delta R, because R plus delta R would be R of T plus delta T. That is the equivalent amount you went further. Now, as your delta T gets smaller and smaller, and this is why they say Q is approaching P, because as the delta T gets smaller, then the point Q gets closer and closer to P, okay? So that's what we mean as delta T approaches 0, delta R over delta T is approaching the velocity vector, okay? And the velocity vector is the instantaneous change of position with time. That's the tangent vector to that curve C, okay? And there it is, okay? So your delta R is approaching the velocity vector, okay? And that would be, oh, so let's see, that's not quite right. The delta R is the difference between the two, and so it's actually getting shorter. So it's approaching the direction of the velocity vector. That's probably what I should have said. Okay. Now, all right. As delta T approaches 0, the direction of PQ, denoted by delta R, approaches the direction of motion at time T. Okay, and that's what I changed mine to say. The delta R is the R of T plus delta T minus R of T, and divide that by delta T, both sides of that by delta T, and that gives you R of T plus delta T minus R of T divided by delta T. Then take a limit of that, this thing here and that thing, as the delta T approaches 0, and that would be the limit of R of T plus delta T minus R of T over delta t. When that limit exists, that is defined as the velocity vector or the tangent vector to the curve at the point P. Just like we had in scalar situations. If you had a scalar function that was your position, take a derivative of it and you got its velocity. But this is making more sense here because, as you know from physics, I think both of you have had that your position vector, which is also called the displacement vector, the first derivative of that is your velocity vector. They're all vectors. So now we're able to talk about them as if they were truly vectors, because they are, and describe them that way. Note that this is the same limit used to define r prime of t, so that the direction of r prime of t gives the direction of motion at time t. That is also your velocity vector at time t. Moreover, the magnitude of the vector r prime of t, is the magnitude of x prime of ti plus y prime of tj, which is, now this is in two space here, is the square root of x prime squared plus y prime squared. Okay, that's the speed of an object at time t. If y'all have had your physics, I think both of you have, you know that's exactly how we define it in physics. Okay, similar to how r prime of t is used to find velocity, you can use r double prime to find acceleration. And notice velocity is a vector function, acceleration is a vector function. As indicated by the following definitions, if x and y are twice differentiable functions of t, time t, and r is a vector value function given by r of t is equal, x of ti plus y of tj, then the velocity vector, the acceleration vector, and the speed are given by these vectors. Velocity vector, v of t, is your r prime of t, which is x prime of ti plus y prime of tj. Acceleration vector, a of t, is r double prime of t, which you could also say, stick in here, v prime of t. That's another way to express it, and that's x double prime of t I plus y double prime of tj, which you could have also said is v prime of ti plus v sub x prime of ti plus v sub x prime of tj, v sub y prime of tj, sorry. Okay, and then the speed, go back to the velocity vector, and it's the magnitude of that vector, and that's the square root magnitude of velocity, or the first root of the displacement vector, and that would be the square root of x prime squared plus y prime squared, the components of that vector. All right, a lot of blah blah blah. For motion along a space curve, now we're no longer in the plane but in space, the definitions are very similar. The r of t is x of ti plus y of tj plus z of tj, okay? And you have a velocity vector v of t is r prime of t, which is x prime of ty plus y prime of tj plus z prime of tk. Acceleration vector is r double prime of t, which would be v prime of t, they didn't put that in here, but it's true, is equal to x double prime of ti, which would be v sub x prime I plus y double prime t, which could also be expressed as v sub y prime of t plus z double prime t k, which could also be expressed as the k component of your velocity vector. The derivative of that, first derivative of that, man, I'm losing energy so fast. Speed, just like before, is the magnitude of the velocity vector, which is the magnitude of the first derivative of the displacement vector, which is the square root of x prime squared plus y prime squared plus z prime squared, square root of that sum, and there you have it. We still got the 3 people. I'm so sorry, I've got to have something else. The nurse was suggesting I not even teach classes and saying, now look, if you get tired, just don't teach. And actually, Dr. Pruitt said the same thing. I'm going to try to slug through it and keep teaching, but I'll apologize. I have to have a little bit of a boost every now and then to keep going. Okay. So here's example 1. This is on page 837, and it's 137, so pretty bizarre. Find the velocity vector, the speed, and the acceleration vector for a particle that moves along a plane curve. We're back in 2 space here, x and y only. C, described by r of t is equal to 2 sine t over 2I plus 2 cosine t over 2j. Okay? Now, pretty straightforward. The velocity vector, I'm going to start over here. V of t is going to be r prime of t, which is going to be the first derivative of this. Well, derivative of sine is cosine t over 2 times chain rule 1/2, and 1/2 of 2 is 1. So that's just going to be I. Okay? Minus, because I know the derivative of cosine is minus sine t over 2 times 1/2, and the 1/2 times 2 is 1j. So there's your velocity vector, v. So this is the A part. The B part is the speed, and the speed is the magnitude of your velocity, which is the magnitude of your first derivative of your displacement vector, which is the square root of cosine squared t over 2 plus, now this is a minus here, but it's the if you incorporate the minus with cosine, with sine t over 2, you know that's going to be then when you square that, square of a negative is positive, so this comes out being plus sine squared t over 2. Okay? But guess what? Whatever function value that is, that's the same here and here. This is 1. The square root of 1 is 1. Okay? Pythagorean identity. Okay? And then it says do the acceleration vector for the particle moving. So we go back to the velocity vector. So the acceleration vector as a function of time is the first derivative of the velocity vector as a function of time, which is the second derivative of the displacement vector as a function of time. And that would be, so take a derivative of this, and you get minus 1/2 sine of t over 2 I minus 1/2 cosine of t over 2j, if I could get my pen to write. Okay, I'm about to lose it again. I'm so sorry. I've been up and down the stairs so many times a day, I don't have much energy left. Plus, I was at Kirkland early this morning, so I didn't have a full breakfast, and then during my first half-hour lunch period, that I have, on Mondays and Wednesdays. I didn't get but a little bit of carrots eaten because I had to make, well, I had a phone call come in, I had to make one go out, and then I had to talk with the cleaning lady because she wanted the full scoop as well. So anyway, it's been that kind of day. So I'm a bit needing some nourishment. Okay, so there is our acceleration vector. That's the C part. Let's see how the book did. The V of t is equal to cosine t over 2i minus sine t over 2j. Perfect. And the speed is the magnitude of that displacement velocity vector, or first derivative of the displacement vector, and that's 1, just like we got. And then the acceleration is negative 1/2 sine of t over 2i minus 1/2 cosine of t over 2j. Now, they do make a little point here. It's in the remark in the margin, the left margin of that page 837. This tells you this particle is going at a constant speed. It happens to be a constant speed of 1, but that's okay. Okay, constant speed. And at a constant speed, this is what they're saying here. Note that the velocity and acceleration vectors are orthogonal, or perpendicular to each other, anytime you're at a constant speed. That's pretty interesting. I know circular motion, that's true. They don't say this is circular motion, but indeed it is. So I'm just not absolutely convinced this is all constant speed motion. I think it's all circular constant speed motion. It may be that it is the other two, but the velocity and acceleration are perpendicular to each other. Now, how can we tell that? Do a dot product. This would give you cosine t over 2, or 1/2 cosine t over 2 sine t over 2, and this would give you, oh, that's a minus 1/2, and this is a plus 1/2 sine square t over 2 cosine t over 2. That adds to 0. And anytime a dot product is 0, the two vectors involved in that dot product are perpendicular or orthogonal to each other. Okay. Now, I think they do a little more. Oh, well, let's see how they did the problem. I'm kind of losing it, folks. Sorry. This has been some sort of day. Okay, first, your velocity vector is your derivative of your displacement vector, and that's t over 2i, cosine t over 2i minus sine t over 2j. Then when you take the magnitude of that vector, the velocity vector, the first derivative of the displacement vector, you get the square root of cosine squared t over 2 plus sine squared t over 2, and that is the square root of 1, which is 1. So that means that anytime the speed is constant 1. And then your acceleration vector, which is the first derivative of your velocity vector, second derivative of your displacement vector, that's your minus t 1/2 sine t over 2i minus 1/2 cosine t over 2j. And all right. Tell you what, I think I'm going to have to go and turn up the heat one more notch. I thought I'd make it through class, and I've got 10 more minutes. My hands are freezing, so hold on just a moment. I'll be right back. All right, the slide set is ready to go to projectile motion. However, the book is not. So let's back up a slide here. Okay, and we'll go to the whiteboard to do examples 2, 3, and 4. Now, whether we get all 4 of those done, I'm not sure. I doubt it, but let's do what we can. Sorry, it's been not a most productive class. Sorry about that. And okay, example 2. I think I'm going to put it in my lap just because it's a lot of glare. We got nice sunshine outside, but it's not that warming. Okay, so here's example 2. Sketch the path of an object. I really don't like this one. Moving along a plane curve given by this. R of t is equal to t squared minus 4 I say I and write J. I don't know what's wrong with the old hand to eye coordination. It doesn't exist anymore, and the eraser doesn't exist anymore either. So I'm just going to have to write this I real sloppily like that. Okay, plus TJ. Okay. Okay. So the first thing it says is sketch the path of an object and then find the velocity and acceleration vectors when t is equal to 0 and t is equal to 2. Okay. Now, I guess we need to do our sketch first. Okay. Now, what I tend to do when I'm doing these sketches, I don't always do this, but when I am trying to do it for a class, I tend to do it this way. Set up, you remember how you used to do t-tables when you're graphing? Well, this is an expanded t-table, okay? Literally a t-table here. You have a value for t, you have a value for x of t, and you have a value for y of t. So this is really a big old t-table, and it can go down as far as you want it to. So let's pick some values for t. When t is equal to 0, your x of t is -4, your y of t is 0. Okay, when t is equal to 1, your x of t is -3, your y of t is 1. When t is equal to 2, your x of t is equal to 0 and your y of t is equal to 2. Now, I think we can get by with those and don't have to go to the negative t's. We could do some negative t's just to see what it's like. I guess we ought to, so let's do that. T is equal, well, but let's just go a couple more. Okay, we'll do 3. Your x of t would be 9 minus 4 would be 5, and your y of t would be 3. Okay, I think that's probably as many as we're going to want to have on there. So let's try at least one negative number. When x is -1, this is still -3. But this will be a -1 then. Okay? I think that may be enough. Okay? Let's see how this looks. Let's draw my axes. Assume that's somewhat vertical and this one somewhat horizontal. We'll do 1, 2, 3, 4, 5, -1, 2, 3, 4, 5, something like that. 1, 2, 3, 4, 5. Goodness gracious, that was terrible. -1, 2, 3, 5. Okay. I think I've lost everybody now. I don't know where people went. It's not time yet, but it's close. I've lost my cursor. Where in the world is... Okay. No, I've still got one person here. Kira's here. I just don't see you anymore. We've lost James. Okay. Now, let's plot the points we got. X, -4. Y is 0. That's 1, 2, 3, 4 negative. 0 on Y. Somewhere right in there. Okay. When t is 1, x is -3, y is 1. So -3, 1 is right there. When t is 2, x is 0, y is 2. There we are right there. Okay? Alright. When t is 3, x is 5. 1, 2, 3, 4, 5. And y is 3. Okay. Now, did we just lose Kira? I don't know if we did or not. This has been really bizarre. There we go. Yep, I'm down to me alone. I don't know why I'm losing people like this. I don't know if my sound is going out. I don't know what's going on, but I'll talk for one more minute, then I'll end this up. Okay. Let's go to the next one. When t is -1, x is -3. That would be here, and y is -1. Okay. So I think I will continue the table for at least 2 more values. T is equal to -2. X is equal to 0 and y is equal to -2. So that would be 0, -2 right there. Okay, and when t is -3, your x is 5 and your y is -3. So 5, -3. There's 5, 1, 2, 3, 4, 5. -3 would be down here. So where is this going? Well, I may have gone a little too far south here. It's going around like this. Nice smooth parabolic curve here. Ooh, that didn't do well. Here, here. And it keeps on trucking. That's the positive direction, so we put an arrow here, here, and this came from back here. Alright. And this, by the way, is when t is equal to 0. T is equal to 1. T is equal to 2. Boy, this writing is terrible. This was t is equal to -1. This is awful. T is equal to -2 and t is equal to -3. Okay. This is fighting a losing battle here. But all the students have left. We've gone a minute over. Okay. So basically what we've done with example 2, we've done the first part, sketch the path of the object. The second part, we'll find the velocity and accelerations, and that's where we'll pick up next time. Okay, we'll pick up finding the velocity and accelerations there. Let me give you some homework exercises here. And these will be any of the odds 3 through 9. They're all at Calc Chat. 3's at Calc View. I think you can do any of, well, let's see. I think you can do any of the odds 11 through 19. They're all at Calc Chat. 15's at Calc View. And we'll stop there and pick up the rest of those next time. I'm sorry it's been such a disjointed day. It has been one for the record books. Sorry that we didn't have a full class. Sorry that I had to interrupt in the middle. It's just not been a good day all the way around. But I'm glad y'all came, those who did come, and those who didn't come, I hope you'll pay attention to this, and we'll meet again the Monday after Thanksgiving. Okay, so we'll see you in about a week and a half. So take care, folks. Well, I'll see some of you later this afternoon, and I'll see some of you tomorrow as well. So take care. We'll see you when I see you. Okay, so I'm going to stop the sharing, end the meeting, and stop the